Independent events seem pretty straightforward, and they are exactly as they sound. Two events are independent of each other if the outcome of one doesn't affect the outcome of the other. Or we could say that the probability of one event occurring doesn't affect the probability of the other event occurring. Where it gets tricky is that we can make an if-then statement about independent events, and we can make it both ways. So let's have a look at what we mean here. We can say that if events are independent, then the probability of A happening is going to be equal to the probability of A happening given that B definitely did happen. Now let's think about what this means. The probability of A, well, that just sits alone, completely separate from B, doesn't it? If I've got two events, A and B, and I just say the probability of A is a third, I'm not even considering B in this part. So I'm saying just what the probability of A is, just generally. Whereas this says the probability of A given a condition, B. Now if the two things are the same, then we're saying that the probability of A happening when B may or may not have happened, we don't even care if it happened, is exactly the same as the probability of A if B did happen. And if they're the same, then the events must be independent. Now it works both ways. If they're independent, this is true. But we can also say that if this is true, then the events must be independent. So we can use this little formula to actually work out whether two events would be independent or not. Now I'm going to jump straight to the last example first. I know that seems a little bit strange, but I think this one explains it differently from the other two. If I toss 6 on a die, that's one event, and the other event is flipping tails on a coin, I can probably use logic without even thinking of a formula to see that those two events are independent, because the die might be over this side of the room and the coin toss might be over here. We can quite clearly see that they're very separate, and just because one thing lands on a 6, it doesn't make the other one more likely to be heads or tails. That's a really easy example to understand. But let's look at how we would actually think this through and apply the formula to prove it. Well, I don't think I would write a Venn diagram to display this sort of data. I think what I'd be more likely to do is draw a tree diagram. If I had to say flip a coin, I could get heads or tails. And if I'm rolling a die as well, then there's 6 options I could get. 1, 2, 3, 4, 5, 6. Or 6 options I could get if I'd got a tail. And I could list all of those, obviously, like this. Now, what we're saying is, if these two events, the coin and the die, really are independent, then the probability of, let's call event A, tossing a 6, it should be exactly the same as tossing a 6 given that we know we got tails. Okay, so what we're trying to prove here is that the probability of a 6 is equal to the probability of getting a 6 given that we know we got tails. Now let's see if that's true. What's the probability of tossing a 6? Well, I could say the left-hand side is 1 out of 6. That's really easy, tossing a 6 on the die. What's the right-hand side equal to? Well, let's use the spotlight method. What's the chance of tossing a 6 knowing that we definitely got tails? Well, that just means we're going to zoom in here and put a spotlight on this section of our tree diagram and ignore all of this part and say, what's the chances that we got a 6? Well, there's 6 outcomes, and clearly getting a 6 is only one of them. It's also 1 out of 6. So yeah, it fits the bill. These two events must be independent because the probability of getting a 6 was exactly the same whether or not I considered getting tails, or whether I definitely actually got tails. So that's one way that we can use the formula to prove that events really are independent. Now with a Venn diagram we can do the exact same thing. To do this we need to understand conditional probability, and remember this means the probability of the first event given we know that the second event has occurred. So the easiest way to do it, I think, is literally just to analyse the left-hand side and the right-hand side. So for this first one, the probability of A is, well, probability of A, well, how many things have we got here? 4 plus 2 is 6, plus another 9. We've got 15 members here altogether in the Venn diagram. So the probability that I draw one thing at random and it's from the A circle, there's 6 things in the the A circle, so the chances are 6 out of 15. Now I can write it as 6 out of 15, or of course I can simplify that fraction and say 2/5. Alright, now let's see what is the probability of A given B. That means put a spotlight on B and say, we want to find the probability of A, but there's a condition, it has to be in the B circle. So we spotlight the B circle and say we're only interested in these 5 items. Now out of those, what's the chances that we randomly pluck out an A? Well, there's 2 members that are in the A circle out of 5 altogether, and that's 2/5. So yeah, I can see that the probability of A is equal to the probability of A given B here. So these 2 events, A and B, must be independent. I can tell it because it makes this statement true. Looking at the next one, what's the probability that if we pluck one of these members at random, it's something from the A circle? Well, how many are there altogether? 5, 6, 7, 8, 9, 10, 11 altogether. How many are in the A circle? 3. So we'd say it's 3 out of 11. That's the probability of A, just all by itself. What's the probability of A given we have to be in the B circle as well? Well, let's spotlight on the B. This is the condition. To play in this section of the game, you only have to be in here, we're ignoring everything else. What's the chance of pulling out a member that is from the A circle out of just these guys? 1 out of 4. Alright, is 1/4 equal to 3/11? No, it's not equal. So we could say that in this example, events A and B are not independent of each other. They must affect each other somehow. And you'll often find in these sorts of Venn diagram situations that they do affect each other. You might like to think through our example that we've used a few times now, looking at the number of students who do art or music. Now, do you think that choosing art might affect your likelihood to choose music? I think so, and vice versa. If you choose art, it might be that you're quite a creative person. Maybe that ups the chances that you'll choose music, or maybe it doesn't. But there's a chance that they are related, isn't there? And to prove whether they are or not, we can have a quick look at it. We know the numbers from this one, because we've done it a few times. The probability of just art would be 5 out of 11. The probability of art, given that we know you do music, well, that would be half. Now, it's close, but not exactly the same. So we can say that those 2 events, choosing art or choosing music, they're not independent of each other. Now, just as you can look at the probability of art given music, you can also do it the other way around. And you can do that to prove the exact same thing. After all, who's to say that these circles couldn't be written the other way around? Now, what you'll notice, we'll just do one in another colour to prove to you that it works. If I'd said down here, all right, let's find the probability of B. Well, the probability of being in the B circle would have been 5/15, which is 1/3. But the probability of B given A means we'd be only putting our spotlight on the A circle and saying, what's the chance that you're also in the B circle? 2 out of 6. And 2 out of 6 is also 1/3. So just as we saw that finding it this way showed that the events were independent, it worked just as well using our sets round the other way.